Welcome back to another video, everyone. Today I'm going to talk about a new technique for solving integrals. It's somewhat similar to the u substitution that I've been teaching you, but this time instead of having u equal some function of x, we're going to let x equal some function of u. To show you exactly what I mean by this, I'm going to be using the integral of 1 over the square root of 1 minus x squared. Now, how can we solve this? Okay, well, let's think. U substitution. Well, if we let u equal the inside of this, 1 minus x squared, there's no negative 2x anywhere else that we can get the derivative of to convert it into a u-world integral, right? So we're going to be doing what's called a trig substitution. A trig substitution is the most common form of substitution where you let x be itself and you let it equal a function of some other dummy variable. We were using u before, but technically you could use v or z or any symbol you want. And in this case, since we're going to be using angles, because, sine theta, tangent theta, whatever, you want that argument to be theta, because that's the traditional variable to represent an angle, and x is already used, right? So let's do that. For this example, we're going to be letting x equal sine theta. Okay, so now how do we find out how to convert from dx to d theta? Well, like this. The process is essentially the same as when we did du dx to find du in terms of dx, except in this time we want to find dx in terms of d theta. By differentiating both sides with respect to theta, we get dx d theta is equal to cosine theta, meaning multiplying d theta across both sides, we get dx is equal to cosine theta d theta. Alright, well, what does this mean for the original integral? Using these two equations, we can rewrite this integral into this. Now we have some more familiar terms because 1 minus sine squared theta, well, if you remember the Pythagorean identity, then you of course know that since cosine squared plus sine squared is always equal to 1, cosine squared is equal to 1 minus sine squared, which is exactly what we have here. This of course allows us to simplify to this expression. Now, the square root of cosine squared is just going to be cosine, right? That's easy enough, right? The root and the 2 will cancel, and what we're left with is just cosine theta, except we already have a cosine theta on top, which means we can cancel both of these out to just get 1 left over. So now, what we have is the integral of 1 d theta. Alright, well, this is a pretty easy integral, right? All we have to do is just theta plus c, right? And then we're done. But of course, every time, theta plus c is correct. However, we want it in terms of x, right? We want to translate back into the x world. Okay, well, same thing, all right? Well, if u was some function of x before, now we're talking about theta, all right? Easy. Theta is just some function of x, right? Well, the tricky part is that we have it written as x is equal to some function of theta, so we're going to have to undo that. If x is equal to sine theta, then that means theta is equal to arcsine of x, which means that theta plus c is going to be arcsine of x plus c. And so, the final result of this integral is, of course, that it's equal to the arcsine of x plus c. Now, this was the first of a few different famous integrals that require trig substitution to solve, and I'll go over the next one right now. This next integral is going to be the integral of 1 over 1 plus x squared dx. Now, for this one, we're going to let x equal a different trigonometric function. This time, x will equal tangent theta, all right? Which means dx is going to be secant squared theta d theta. All right, so what does that mean for us? Well, this new integral is going to be 1 over 1 plus tangent squared theta, my fault, times secant squared theta d theta. Now, 1 plus tangent squared is actually another trigonometric identity. Now, if you don't know all three of them, I would suggest just looking at the sine squared plus cosine squared equals 1 and dividing by sine squared or dividing by cosine squared and seeing what you end up with. You'll see very easily why this identity is true, that 1 plus tangent squared must equal secant squared. What that means is that our new integral is going to look like this, secant squared over secant squared d theta. Now again, this is just going to cancel out to be 1. The integral of 1 is just going to be theta plus c, except theta is equal to arctangent x, which means this integral is equal to arctangent x plus c. It's essentially the same process as the last integral. It's just you sub in tangent instead of sine, and you use a slightly different trigonometric identity to finally simplify everything. But the overall ideas are the same. Something I want to talk about is a slight variant of this integral. 1 over a plus x squared dx, where a is not necessarily 1, it's just any positive real number. Okay, so how do we do this? Well, we're going to do something very, very simple, but also very clever, right? If we want it to be 1 plus x squared instead of a, well, why don't we just factor out the a? Let's try it. This is equal to 1 over a times the integral of 1 over 1 plus 1 over a x squared dx. Okay, well, we've got 1 plus something times x squared, right? How does that help us? Well, we just change up how exactly we use our substitution. We're going to be letting x equal tangent theta again. However, in front, we're going to be putting this, the square root of a. Now, what this allows us to do is when this x gets squared, this square root of a is going to get squared. It's going to be a normal a, and it'll cancel out with this 1 over a, right? Now, dx, in terms of d theta, the square root of a constant will not change, and we'll get this secant squared theta d theta. Okay, so what's our new integral? Well, taking everything that we know, we're going to go from this integral to this one by first, this x squared is going to be a tangent squared, right? The square root of a gets squared, it becomes a. Tangent gets squared, it just becomes tangent squared. So we have a tangent squared in place of this x squared, and then still that 1 over a. And then this dx becomes square root of a secant squared, that's right here. And then this d theta gets added onto the end. Now, we can simplify this. First of all, this square root of a can come in front, and the coefficient in front of the integral will become 1 over root a. And then this a over a will cancel to just be 1. You don't have to worry about that. And we'll be left with 1 plus tangent squared. 1 plus tangent squared, of course, is secant squared theta, sorry. This, of course, becomes just 1. And then the integral of this is going to be 1 over root a times theta plus c. Okay, so now we just have to translate from theta back into the x world. If our expression is 1 over root a times theta plus c, well, we know from this, dividing by root a on both sides, we get tangent theta is equal to 1 over root a times x, and then theta must be equal to arctangent of x over root a. This means that this expression becomes 1 over root a times arctangent of x over root a plus c. And this would be our final answer. Now, you'll most commonly see this in a textbook. Remember, this integral was 1 over a plus x squared. But mostly, if you're looking in like a textbook or something, they'll have this as already being squared, some number squared, which makes the formula, maybe it makes the formula a little easier to remember, but it just means that these square roots of a, well, when you take the square root of a squared, these square roots of a just become a, right? So it's the same thing, it's just, maybe it'll be easier if you remember that a is a number squared, and so this will be the general formula. But if you want to just derive it, solving it by ourselves like we did here, just thinking about it as a, honestly, I think makes it easier. But this is the idea behind a trig substitution. You take something where you can't exactly reform it or make a u sub, and you instead realize that there are ways to set up identities to convert one expression into another, which allows everything to reduce down, and then you're able to solve it. I'm hoping you guys were able to enjoy this video. I really hope you learned something, and if you want me to go over more examples of this or talk about it more in depth, let me know in the comments. And as always, thank you guys so much for watching.